So all this started about 3 years ago when I was looking into sort implementations, and I was curious as to like what kind of different implementations were out there, how they could be compared, and maybe even writing my own or adapting an existing one. And so I started with writing a test suite first, and I also was working on a benchmark suite for like figuring out how all of these existing implementations would compare, and maybe even when I make changes, how that would impact those implementations. There's also something important you need to know, that is modern sort implementations are not a single algorithm. So it's not just merge sort, insertion sort, or whatever. They're hybrids. So they use different algorithms in different ways to tackle the different nature of the data you can get. For example, you can get something that's completely random, or you can get something that's nearly fully sorted, and just the last couple elements are new because you have a vector. You just pushed a couple elements, then you call sort again. You push a couple new elements, and you call sort again. That's a common pattern you find. And also, modern CPUs are extremely complex. So like predicting performance is nearly impossible, and you want to measure it. So you need some benchmarks, and then this benchmark produces data, and you want to somehow visualize that data. So that's where this came from. So let's first look at the problem space. There are multiple dimensions to this problem space. So for one, you have different patterns. As I talked about, random, maybe a Zipf distribution, nearly sorted, already completely sorted. That's also a common pattern. Then the input length. So maybe you're sorting something very small, maybe 20 elements, 2 elements, 5 elements, right? More than 80% of the calls to sort, maybe more than 90% of the calls to sort are actually for things that are less than 2 elements long, right? So if that's super slow, that's maybe not a good idea. But even in the middle, that's maybe interesting. And maybe you have something very big. So all these things matter. And if you're writing something generic, you can't choose your application, right? If you say, yeah, I know exactly what my input is going to be. OK, but maybe your domain is I'm writing this for a standard library, and then you have no clue what your data is going to look like. And the CPU prediction state is also quite important. That's, for example, the L1 data cache, L1 instruction cache, branch target buffers. All of these play a role in how prepared they are, how well trained they are, how hot or cold maybe it's called. These caches are, and that's another dimension you can change, right? You can maybe say, okay, I'm going to flush my branch target buffer, but I want to keep the data buffer, the L1 data buffer, intact and see how that affects it, or maybe another combination. Or that's another dimension to explore. Also, which implementation are you looking at? That's also another dimension. And which test machine are you on, right? They are different. I could test on this laptop. I could test on a small embedded chip, on a server chip. They all have different characteristics, and they will also impact these benchmark results that we're going to look at. So, I mean, we have a couple dimensions. What are we going to do? I think this is the intuitive solution here, right? We have a 5-dimensional problem space. So let's do a 5-dimensional plot or a graph. This is a 5-dimensional cube flattened down to 2-dimension. I think it's quite intuitive. I mean, of course, I'm not serious here. So let's try to reduce the problem space. We have different dimensions, but we don't have to look at all of the dimensions at the same time. So maybe let's pick and choose different ones and look at them in kind of a sliced fashion. The input pattern, like I'm going to show you one specific visualization, but this is just one way to choose different dimensions here. I did choose different ones in a different context as well. This is just for the purpose of comparing 2 implementations. So I want to see what are the improvements, what are the regressions. This is the kind of message I want to find out with the graph we're going to look at. So the input pattern, I pick a couple diverse and representative ones. So they should highlight different areas, strengths and weaknesses, but they should also be kind of realistic. There shouldn't be something that's only going to show up in a synthetic like benchmark. I care about real-world performance, and these are synthetic benchmarks by nature, so making them even more synthetic is not what I want to do. I want to make them as representative and informative as possible. Again, the goal, the area is something very generic, general purpose. The input length, that's also super important, right? If you don't know who's going to use you, maybe they're going to do a rolling median, so they just call you with like 10 elements each time, or you're going to be called with 10 million elements. The whole area in between is important. The implementation, as again, we're looking for regressions and improvements, so we're going to pick 2 and compare them against each other. And CPU prediction state and test machine, these will be not included in one set of data, but it's going to produce multiple graphs. So these are out for now. Okay, so concretely what we're talking about, it's about 7 input patterns, 30 length steps. We're looking at 2 implementations. That's about 400 data points. So that gives you an idea of like how much data do we need to visualize? What are we looking at? There's a difference if you want to visualize 5 points versus 10 million or 400. Like this gives us kind of a mental space so we get an idea what we can show. So what I did was I had a rough idea of what I wanted to show. I knew the kind of data I would get. I had already ran benchmarks. I had the data. I knew kind of the dimensions I was going to look at, but I had no good feeling for how to visualize them. How do I turn all these how do I turn that into something you can look at and get an intuitive feeling, right? That's the purpose of a graph, of some visualization, using the high bandwidth connection to our brain, that's our eyes, and telling us something. So I asked a previous colleague of mine, if he had an idea. And he came up with this, right? So you have a relative improvement, right? You say, okay, one is faster than the other, or the other is faster than the other. And then you plot the difference in some kind of like balloon fashion to show where the area concentrates, where the data concentrates. And that's a good idea, but it wasn't quite what I was looking for. So after some back and forth, he sent me this picture, right? Like he drew it on some paper and sent it to me. And the idea is you take a combination of an input pattern and input length, and then you look at the 2 data points you have. For example, one took 1 millisecond to compute it, and one took 2 milliseconds to compute the same result for this one input pattern and one input length combination. And then you compute the symmetric difference, the symmetric speed up. So the one is 2 times faster than the other in this case. And why is the symmetric speed up? That's quite important. If we do percent increases, it's not symmetric. Something that is 100% faster is 50% slower. So like usually that's not symmetric, and that's kind of weird. So it matters which way you look. But if you make it so always one side is X times faster than the other, and you always pick the side on the graph based on which one is faster, you can get something that symmetrically shows all the data without giving you a bias. Right? So it doesn't matter which way you flip the graph, you get the same graph, just mirrored essentially. And that was I gave him some test data, and that's the first thing he sent me, right? Okay. But actually, it looks confusing, but there's more to see here than just meets the eye at a first glance. For example, we see that, yeah, actually most of the benchmark cases neither regressed nor improved, right? Most sit around the middle. So there's not much to see. But actually, we see on the right side, we see a curve where we say, okay, maybe some data is clustered there. On the left side, we see, okay, there was quite some regressions, especially for smaller input sizes. Then he also drew a mean actually in there. And we can see you could make the argument that in total, assuming all patterns are representative and all patterns are weighted equally, it's a total in total, it's an improvement. The more things get better than things get worse. Actually, with like 400 data points, not a terrible message to send, but it's still quite unwieldy. So this was a long time ago, and over time I improved this graph, and I made changes to it to make it more readable, more understandable, more helpful. So first I took this thing and ported the idea, the logic, to a Python framework called Bouquet, but it's not an important part here, right? It's just a tool to get to the means. I wanted to visualize the data, and it was a ready-made tool with existing support for the kind of graphing needs I needed. They didn't have the specific graph I wanted, but like building graphs was quite easy in it, and I had some experience with it, so that's why I used it. Feel free to use whatever you want to use. So there are a couple changes. First, I rotated the graph, so now if it's humans are a bit better at recognizing a straight line if it's horizontal instead of the other way around. So this makes it a bit more user-friendly, I would say. And the other thing I changed is that points are now transparent. There's some transparency to them, and this gives us a possibility to see clustering of points. And I didn't draw the mean line, but I specifically highlighted the points that represented the random pattern, because I thought it was of special interest. It's kind of the normal thing you benchmark sort implementations. Again, the random pattern, the other stuff is more of a nice to have for many people. So that's the next iteration that we see. We also get to have a axis that is labeled. Both axes are labeled. That's important. And And this was an interactive graph. So I could open it in my browser and look at the individual points and get an idea of what each point means. For example, I could see this one in the middle, that's this pattern. But if I just look at the picture, if you look at this picture right now, you have no clue what the patterns are, right? You only see the random pattern, but everything else is basically opaque. So this was the next iteration. Also, I want to highlight this is a different data set, right? We're going to look at different data sets. Each picture is a different data set, but it's the same idea. And why am I not picking the same data set? Well, because I try to limit myself to actually graphs that I published. All the graphs you're going to see are the graphs that I used and published to talk about my work. So you see the real progression I made over the years with this graph. But this also means it's different data. Here we see the regressions are way fewer. Earlier we saw a huge amount of regressions on the left side. Now we see relatively fewer regressions because the implementation, my work, improved over time. So this is the next iteration we see. We see quite a lot of changes. For one, each pattern now gets its own color. So you can differentiate the colors, the patterns by color. The color palette is a specific one that is designed, not by me, but by other people, to be friendly to people that are colorblind. So it should be possible to discern this just by the color, even if you're colorblind, but more on that later. The axis also a bit more changed. I include now which machine it was tested on, because again, it's a dimension I added later on and wanted to differentiate the graphs, be able to look at a graph and know which machine it came from. The x-axis, so the input length, also now goes to 10 million elements, not only 1 million elements. This goes past the L3 buffer size, so we get roughly a quite complete picture. Past this size, the only thing that matters is the memory bandwidth, and all the algorithms will be equally slow, more or less. So mostly that's a good range to look at. For our specific domain, if you're building a database, sure, that matters, but not for me in this case. Also, it's the line where it's the equilibrium point, essentially. That's put in the middle now to be a bit more fair, right? Here, this favors one side than the other side, so I was like, no, let's be as fair as possible. If we flip the graph, it's just going to look mirrored. It was so before, but now it's even more so, and it's at the middle now. And the title becomes unique and machine parsable and whatever, but these are just small things that changed. Okay, so this is the next iteration. I made the graph wider, so it's more easily readable. And then the major change is I switched on the left side from, what does that mean? Okay, it's percent improvement, but it's kind of confusing because 80 means it's 1.8 times faster, and 200 means it's 3 times faster, and minus 200% means it's 3 times the other one is 3 times. Okay, it's kind of confusing. Just write those numbers there. It took some figuring out how to actually put them there because the library didn't foresee us using it this way, but eventually I figured it out, and this makes it much more readable. Yeah, it's 1.8 times faster for this combination, input length, pattern. You can see it. Okay. Also, I redistributed the points in the log space to be more, let's say, more evenly spread out, to get more information about the entire space, not as bunched up as here, where I just picked human-friendly numbers. You see 10,000, 100,000, million, whatever. I add some more points in between. I keep some human-readable points, so 1 million, 10 million, 100,000 stay in there, just for ease of use. But let's say there are other points in between that try to be put inside this logarithmic space to exploit more thoroughly. Yeah, and operating systems also added because I noted, okay, yeah, maybe there's some implementations where operating system matters, and I wrote a whole thing about that, and it's there. Okay, so the next iteration. I improved the render resolution. This is kind of blurry. It gets sharper now. I improved the render resolution of the graph, and the major difference is each pattern now gets a symbol, a unique symbol that shows us, okay, maybe we don't even need a color. We can just look at the pattern and look at the symbol and get a feeling for, okay, to differentiate them this way. Even if you're not colorblind, I'm not colorblind, but even then I find it makes it easier to understand, easier to read, and also exclude some color. There was a bright yellow color that I found had a poor contrast with the white background, so I removed that. Also means one less pattern, 8 to 7, so less data, a bit easier to read. There's also zoomed in. It's not always plus 3 times to minus 3 times. It's now zoomed in based on the data, min max essentially. Yeah, this is kind of the final version I landed on some time ago. I fixed a unique symbol bug, if you spot it. Random Z1 and random P5 have the same symbol. They were supposed to have different symbols, but now they have actually different symbols. So again, this is all different data, right? We're looking at different data sets, different things. You can look at the top if you're interested in whatever I'm comparing there, but it's not an important part here. And I changed the zoom in to follow a specific curve. So I configure and say I want to look at the random pattern, and I want it to be fully visible, and everything else can clip out, because you see there's some major outliers that go to up something like 10, 20x or something for one specific data point, because it's some algorithmic edge case that it's hit, and it will just make everything else very hard to read. And so this is from a workflow. If you generate hundreds of these graphs, trust me, this makes it a lot easier, your life. So let's go over to something where this is what you usually get in contrast. So this is not just something random. This is from Andrei Alexandrescu. You know him probably. He gave some talks here, or some of you know him. You don't have to know him. But he also wrote about sorting, right? About branchless partitioning and whatever. And so it's kind of the same domain. So I thought, okay, maybe it's a fair comparison. And what you get is a bar chart. We get 1 million to 10 million in increments of 1 million, and 4 implementations compared. On the left, on the y-axis, we have, I don't know which value. It just says 400 or 500. Maybe it's milliseconds, who knows. On the bottom, it's input size. And then we have the different colors. So for one, you can only differentiate the bars by understanding and seeing the color. And these are not specifically chosen colors for colorblind friendly. So maybe that makes it a bit harder to understand. But even more, I think, impactful is if we put the same data, if we take 2 implementations out of this 4 and graph it into the thing we just graphed earlier, the same pattern, not same pattern, but like the same plot essentially, we see a couple of things. So for one, picking human-friendly input sizes usually leads to over and undersampling your input domain. We see there's a huge gap between 1 and 2 million, and then between 6 and 7 million, yeah, okay, sure, fine. They're super close to each other. It's probably not very interesting what we're going to learn, but we spend time computing these benchmarks, right? A graph like this can take a whole night to compute, right? Like sometimes if you do statistical benchmarking, so you just not run it once, but you run it until you're sure enough that your data you're getting is actually significant. Each data point can take, 6 seconds, and then you need 2 of them, so maybe 10 seconds and more, and then you have 400 of them. It takes time, right? So I can get why you don't want to produce this all the time. There are faster ways of producing similar graphs, but essentially what we're seeing here, maybe if you have something very simple, this could be a good approximation. But I think even more so, we have complex adaptive algorithms that are not single algorithms. They're hybrid algorithms that change based on the input pattern, input length. All of these are these matter in the real world, actually. And just this, I think if you see here, it tells us a very limited story about what this impact is on the performance by switching from one partitioning to another, partition algorithm to another here. Maybe there are some hidden areas we don't know about where it regresses or improves even more, but we don't know because we didn't measure it. Yeah, and with that, let's recap. So all this started out as this like sketch by a colleague of mine, and it evolved into this graph. A lot of love and work went into this idea. I went through many iterations. Looking back, it was time well spent. I'd do it again. It helped me really understand the complex trade-off space and design space in this area. And I encourage you to also, like, if you want to do something like this, where you really write your own custom visualization for something, maybe benchmarking, carefully think about your domain. So this plot, this graph, is not the solution for all graphing needs. It's just there for my special need I had, and it's there to help me fulfill my goal of understanding how it impacts certain things. Don't just take this code and think, oh yeah, I'm gonna do the next visualization with this. The important part is, as we've seen at the beginning, think about your domain. Think about how you can reduce it to important and interesting parts, but still keep it data rich. You can see we can show 400 data points because we combine 2 of them into one. It's only 200 essentially, but still we can visualize 400 data points in a way that's helpful and immediately understandable. You can see, okay, yeah, something happens with random P5 or down here. Also, a good visualization with bad data is still useless, or maybe even worse, misleading. So make sure your data is good first, right? Or maybe continuously, don't throw at it some data and think, yeah, sure, it's going to tell me the solution to whatever I'm doing or the answer to whatever I'm looking at. And please keep in mind, benchmarking is hard. Benchmarking is incredibly difficult. There are so many pitfalls. And this talk is not about benchmarking or how to do benchmarking. That will be a much longer talk. Yeah, so let's recap here, a couple of links for you. The first is the repository where you can find the code that includes the visualization, also this repository. But keep in mind, this is code I wrote for my very specific needs. So if you want to use it, fork it, feel free. But if you want to upstream something, sure, if it's a bug fix, do it. But it's not there to be a general purpose framework. It's a very custom built solution for a specific problem, there to make me happy. That's the whole goal of this thing, right? It's not there to make you happy. Okay. The talk repository contains the slides if you're interested, and I talked about a colorblind friendly color palette. There's the link to that. And with that, thank you.